Okay, we should start. So, welcome back, everyone. So we have the second section of the workshop. So we have our next invited speaker, Kristen Grauman. Um, Let me introduce her. So Kristen Grauman is a research scientist at Facebook AI Research and a professor in the Department of Computer Science at the University of Texas at Austin. Her research in computer vision and machine learning focus on visual recognition, video, ego-centered perception, and embodied AI. She received her BC at MIT in 2006. She is an IEEE Fellow, AAAI Fellow, a Sloan Fellow, and the recipient of the Computers and Talk Award. She and her collaborator have been recognized with several Best Paper Awards, including uh, 2011 Math Prize and 2017 Helphorn Prize. She served a program chair for New Reefs 2018 and CBVR 2015, and is also an associate editor-in-chief for the transition of pattern analysis and machine intelligence. So here, without you, we are very happy to have Kristen Grauman to give us an invited talk. So welcome, Kristen.
Thank you, Du. Thanks for having me here, and looking forward to sharing this work. So I am going to talk about object affordances and learning how people use objects from video. And I think this fits with the theme of the workshop in terms of moving away from caring about only things we can name and producing names for them in a closed world towards a broader understanding of objects, even those we don't identify by name, or in my case here, the ones that we understand better because we know how to use them. So this talk is motivated by problems in embodied AI, where you have agents that need to operate in human spaces. So imagine the robots of the future that you could talk to and ask for help with things like, could you heat a cup of tea and bring it to me? Now, if you have a robot who's faced with such a challenge in a human environment, they have to do a lot of things to solve it. So they have to figure out what are the steps of this activity, what objects are involved, how do you find those objects, the ones that the person named, but also functional things like, can I heat this cup? Where would I go to heat it? How do I grasp the cup? And so I want to make this contrast between the traditional recognition part of the task, which would involve knowing what things are called and what they look like, versus all these other parts that have to do with how things work and how to interact with objects in the world. So that's kind of the bottom part is what we're trying to pay increasing attention to. And again, this really seems to demand open world understanding of the environment and of the objects in it. Now, the approach that we're going to take is to accelerate how well we can learn about those questions by watching people, especially watching them in video and especially watching them in egocentric video, like in this head-mounted camera video I'm showing here. So what do people reveal when we see through their eyes in a video like this? We can find out how they move in the environment, how they're directing their attention, how they interact with people, and most importantly for the talk today, how they interact with objects. And these examples show that very well. So in general, we're looking at different ways to translate video into action, where the video is going to inform agents that are trying to learn to do tasks in the human world. So we're working towards these embodied agents that learn by watching people interact with environments and the objects. And I'm going to talk about three examples from our recent work to illustrate this. The first one will be about interaction hotspots, being able to find an affordance map on an object, even an object from a category that we haven't seen before. Then I'll talk about our new work on activity context, being able to learn from video how people bring objects together in a useful way so that an action can even happen. And then finally, the third part, I'll briefly comment on our work, looking at how people grasp objects and new objects and how we could learn from video how a dexterous robot hand could do the same. Okay, so three parts in the remainder of this talk, and let me go right in with the interaction hotspots. This is where we're getting right to this question, how do I go beyond naming the lamp as a lamp and instead understand how to use it, where to touch it to achieve any different goal, like adjusting it or grasping it or toggling the switch. So we'd like to be able to see objects through that kind of lens. Now, if you look at the literature, including current and recent approaches for tackling this object affordance prediction problem, often people are using really semantic segmentation approaches that are trained with supervision consisting of regions that people have drawn to say, here's where I would hold a book, for example, or here's where I would turn the page. And this can be moderately effective or reasonably effective, but has a couple of key drawbacks. One is the cost. Of course, we don't love labeling things in order to teach in a really heavy supervised way. But even more important, there's this gap because you have the fact of how someone holds a book versus how an annotator would be able to express it to you with a mouse and to draw such kind of training data. So we've been exploring a different approach where we take that idea of learning from people and see, can we learn affordances from video directly? Okay, so this would get rid of that gap and would allow us to see how people are holding books or any other activity and try to convert that into our predictions of affordances, both on objects that are familiar as well as objects that are new. So let me talk a bit about how we've approached this to start. First, we think of weakly labeled video data. Weakly labeled in the sense of affordances, there's not going to be any hand-drawn maps. Instead, it's going to be temporal segmentation of actions with actions that are present. So from such data, we can start by training an action recognition module. Here is an LSTM looking at the frames of the video, and it's able to classify whether we're looking at open or close or press or pull or any other of the affordance actions that we want to understand. Now, so far that's just action recognition, but what we'll do is augment this model with a module that does anticipation, trying to predict what is the state of the object when it looks like it's being opened from pictures of the object when it's at rest. Okay, so this is very important for affordance because affordance is the potential for action. It's not recognizing the actions happening now. It has to be that I see the object before anyone does anything with it, and I can anticipate what actions are likely possible with it. And so this is the kind of network we build to do that anticipation. And again, we're in training, we'll not only learn how to recognize actions, but we'll learn how to map objects at rest, like this microwave on the top left, to those hidden state of the open-like action or any other action. Okay, so this will be a model that you can give video and it'll give back anticipated affordances. Now, to make those localized in the pixels of the object, what we do is use a class activation mapping approach in that same network I just showed to go back to the image of the object at rest and identify those spatial regions that are most responsible for the anticipated action. So in this example, the object's the refrigerator, and here are the places that we would flag as looking pullable. And if we do the same thing for another action category like press, we'll go back and find those parts that look pressable. Okay, so this is a short version of what we call the interaction hotspot approach for finding visual affordances on objects. And I will show you some examples, results with two data sets. One we've trained with Oprah, which is some YouTube product demonstration video in a Stanford data set. And the other is from Epic Kitchens, which is a first-person data set of unscripted activity in everyday homes and kitchens. Now, very importantly, especially given this workshop's topic, we're going to train on these and then generate heat maps on novel images, not just from new instances of objects, but even new categories. And this is what's really important about affordances and thinking of objects as things to use. We don't have to look at them only in buckets of names, but you can show me or you can show the system a new object category. And so long as it has visual resemblance in its function to different other categories we've seen, we'll be able to generalize. So here are some hotspots. They're color-coded by the action name. So that stuff in the bowl looked mixable before the person mixed it. Same with that pot just behind it. And here I'm just showing the ones that are most common occurrences of verbs in a set of some dozens of actions. Here in the sink, something looks washable. The knife to the side also looks washable. Here, the pan looks mixable. The jars look openable. Before we get to that door, it looks openable as well. So you can see how, no matter what these things are called by name, there were no object annotations in this training, but we're able to understand objects for their functionality because we've learned by watching the human action. Here's a final video in this set where we're contrasting saliency on the left with affordances on the right. And the color coding means, we have that extra information. It's not just what looks interesting, it's what we think we could do with it. We being the agent, the eventual agent trying to use these affordance maps. Okay. So interaction hotspots then, I've shown you kind of qualitatively what they look like. We've also evaluated them systematically against human given ground truth for the 2 data sets I mentioned, thinking about how well we can do versus other weakly supervised models with different types of supervision, as well as the strongly supervised models that are performing more of a semantic segmentation. And in all, the results are encouraging, especially in terms of the gains we get with respect to other weakly supervised models. Now, there's one more result on this I wanted to share, which is thinking of how functionality of objects and objects that we haven't seen, including objects we haven't seen, would allow us to do better recognition. And people do this because we understand more quickly what we're looking at if we understand how it works, how it functions. But we wanted to run an early experiment to test this with the hotspots. So here are refrigerators that are hard or easy to detect, easier on the left and harder on the right, with an off-the-shelf model trained to do object detection. Now, what makes them hard? Well, they're unusual contexts or views. So our idea was to augment the encoding of those objects to show the affordances as well. So take the hotspots, use their feature space to augment the feature space for these objects, and see if this will improve recognition, particularly in the low shot setting. So in other words, if we've only, this is some new object, and this kind of relates to this open world problem where maybe I've only seen 5 snapshots of it with a label, and then we want to be able to generalize and recognize it in other images. This is always a hard problem, but what these early results show is that if we use this notion of function to augment the representation, the accuracy of recognition actually does improve in this few shot setting. And this is early result, but promising because it says that there is not just the utility of understanding how things work for using them, but even for recognizing them. Okay, so far I've talked about interaction hotspots. This is looking at objects to find out where to use them and how. I want to take this a bit further and now talk about activity context for addressing tasks in what's called visual semantic planning. So here I'm going to have agents that work in, for now, simulated worlds like AI2 Thor. That's where these videos are coming from. And they're given tasks that are sequential in nature, so they require some number of steps. And the agent is trying to use its egocentric visual stream in order to understand the environment and reach a goal state. And so a goal state can be something like, make dinner or get the trash into the trash can or clean the kitchen. These are just some examples, 7 different kind of goal states you might want to reach. And notice that an agent solving these is both going to have to move in the space to get to the right parts, but also interact with objects, like pick things up, put them down, slice them, wash them, things like that. Okay, so this is the problem space, and I'm still thinking of it in terms of how can we learn from people in order to make this task succeed more or be learned faster. And the reason you need to think that way is because traditional or even really current approaches to tackle visual semantic planning and to build interaction policies are often grappling with sample efficiency. And that's because if you take a reinforcement learning approach to the problem I just described, there's so many action sequences you could take, and only very few of them are going to land you with a reward of succeeding in the task, meaning getting the environment to that goal state. So we know that sparse rewards are a big problem for the reinforcement learning agents trying to tackle these interaction tasks. One way people try to improve the situation is by incorporating demonstrations. So this is another way humans can help robots learn, by just showing examples of how the task can succeed. And this can speed up learning and is often used. A problem is that it can be a little bit awkward to provide these demonstrations. In the case I just showed you, it would mean kind of inhabiting that virtual world, and doing some traces of the motions and the interactions and so on. So very hands-on kind of approach. So to contrast to these, what we're going to explore is how we can get these activity states, meaning these complex configurations that are preconditions to solve a task, from human video. So for example, a complex configuration needed to solve this washing task would be that the agent needs to get to the sink. There's got to be the dishes there for washing. He needs to be holding a sponge. Soap needs to be there. The faucet needs to be on. And this all sounds very basic for a human actor, of course, but for an agent trying to discover that these are the things that make the task work, this is a lot of complexity. So how can we help them reveal this? Because if any part of that puzzle is not there, the task just won't succeed. So again, just like my previous example, we want to know, can we learn this from video? Just watching people in egocentric video do household tasks where objects, come together in appropriate ways to enable the task at hand. And what this video is showing is how, if we find objects of interest, we find the ones that are touched by the human hand and understand their typical relationships to other parts of the scene, this might give us just that activity context we need to learn. So then, building on that intuition, the idea that we are putting forward is to discover from in the wild egocentric video which objects together enable an activity. So think of it as watching video in order to discover the preconditioned states that enable a step of action for an agent working in the world. We'll watch egocentric video, find out what these objects are and how they're compatible, with what degree they're compatible to achieve different tasks. And then we'll leverage those compatibilities or those activity contexts to guide the policy learning. So for example, maybe here we would pop out from the video the fact that pans were relatively useful in combination with the stove or the sink, but not these other things. That means we can take this info to an agent operating in the world who, at the time it's holding a pan, will now have a preference for where to go explore to find useful interactions. And I should stress this will be in a task agnostic way or a task generic way, because we'll learn these kind of activity contexts across activity class boundaries so that when we're faced with a new visual planning task, like go do the laundry, then we won't be starting from zero information about how to bobble around the scene and figure out how laundry gets done. Instead, we'll have agents that are drawn to do and put themselves in situations that bring objects that are useful together, just like humans would in a real environment. And this will speed up learning. So I want to contrast the kind of graph I just showed a moment ago, which is our idea to learn from video, these activity contexts, with other kind of object relationships you might learn in the literature. And that includes affordance priors from our own work, like on the right-hand side, as well as scene label priors or semantic word embedding kind of priors that are capturing things about how objects relate in terms of their static properties or their spatial layouts, but not capturing a notion of human use. And this is what the activity contexts are really trying to zero in on. And that's why it's important to learn them from video, as opposed to, say, snapshots or to WordNet or other kind of ontologies for object relationships. So let me say a bit more about how this approach works for activity context. We'll have ego video, which has temporal segmentations, but no action labels. Okay, so there's kind of chunks of video where people are doing something, and that's what those colors show. And then from a given clip, then we're going to look at the frames, detect objects, any objects that are there, and then isolate those that seem to be involved in the person's activity. And this means those that are having some hand-object interaction and that are close by to that interaction. And that allows us to separate things in the background that are just there but not being used from those that are really part of the action itself. We further will filter that list to kind of eliminate those that are not movable. So the interacting object being the plate, that's something that's movable and manipulatable. And so those are the kind of objects we're going to concentrate on because they're driving the action. So now imagine doing this over all sorts of training video to understand how people seem to be using objects together. Then we'll come back with these activity context frames and examples from which we can compute holistically over all the video some what we call activity context compatibility scores. And that's the score at the bottom that's going to relate any two objects, OI and OJ, based on how likely they're brought together during an activity. Okay, so this is where we're getting a human leg up. So the view from the video, that's a jump start for the RL agent that's going to learn how to do things in the environment by understanding that these are the kind of things a person would prefer to get together in order to do a step of some action. So what it looks like for the agent then is here. Agent's going to be looking in its egocentric view, finding objects, picking them up. Here it's picked up a mug, and now an agent that gets that mug towards a faucet or a sink is going to be rewarded simply for doing that because it's starting to witness the kind of preconditioned states that were useful in general human activity. There, it was also rewarded for getting that pot on the stove, no reward for getting a knife in the garbage can. Okay, and I gotta stress, this is all, at this point, task agnostic, right? It's just saying, here are things that when you're starting to explore how to use this space and to solve a new task, you would be in good position to start trying in order to discover with a denser set of rewards, what is the way to solve the task. So that's exactly how we implement it. We build a reinforcement learning agent that views the RGB video stream, remembers all these activity contexts learned from human video, and augments the task reward, which says, is the laundry clean or not, with the reward for the activity context objects. Now, when we do that and test across a number of different visual semantic planning tasks, here I'm showing all 7: cool something, store something, heat something, etc. Then we can compare the model we propose, which is in the bottom row, and its relative success on addressing these tasks in new environments with models that do more traditional reasoning about object relationships, like scene priors based on co-occurrence, or that do more traditional or current things for exploring the space and augmenting the reward with a preference for discovering new interactions or a reward to prefer visiting new objects. And overall, the results are promising to improve the success rate, especially on those tasks that are more challenging on the left-hand side, and more challenging because they have a greater sequence of steps that need to occur, and this makes it much harder to stumble upon the right way to do it. And this in turn will accelerate learning, and that's what the bottom chart shows. As you spend more time training, you get better, but you'll get better a bit faster, a good margin faster, using this activity context idea. Okay, so I've talked about object affordances and then kind of higher order affordances, how we bring objects together. In the last couple of minutes of this talk, I want to talk about our new work on grasping objects, and again, learning from people how to do it. And we're specifically interested in this case at a finer grain level of interaction, a dexterous hand. A robot with a dexterous hand is appealing. That dexterity would open the door to new tasks beyond even grasping. But of course, this is a very highly complex action space. There's 24 degrees of freedom on this hand. Now, the hand is like a human hand to a certain point, so we can look to humans on how they use human objects that are built for human use, like these examples are showing. And in fact, we were looking at this from two sides. We want to understand from video how people grasp, like what's the 3D hand pose they use to pick up a given object and use it, as well as human affordance regions, like the hotspots I showed earlier. And so what we've done in this work is to bring in both those factors to an RL agent that's learning how to pick up objects in a functional way, both to prefer to pick them up where the object affordance region is, and to do so using a grasp that is close to what a human would do. So the way this happens, as we'll see in a moment, is to basically augment the reward to prefer those kind of settings. And this will allow us to learn to grasp new objects faster. And here, again, the open world does come about because you have new objects that you can still predict affordance maps for it, even if you don't know what they're called. And this will help the agent know where to pick them up. So we get our pose priors from how-to videos, and we use an existing pose estimation model called Frank MoCap to get those hand poses. And then we can summarize them across the different instances we've seen. So those were examples for a cup. Here's examples for a hammer, and you can see the kind of trends and how people are using their hands. And now we build a reinforcement learning loop that does, as I said a moment ago, it's going to encourage not just getting the thing off the table, but doing so by touching the affordance regions and using a human-like pose. And here's that agent at work starting to learn early on, how do I get these things off the table, and trying to do so in a human-like way. And as training goes on, it gets better and better, and can start picking up these objects, even objects it hasn't seen before. And indeed, the learning's faster. So the top curve there is the video prior that I was describing, including the hand pose. And this is getting you a higher success rate with much less iterations and experience by the robot compared to other things you could do, including a state-of-the-art imitation-based reinforcement learning approach that's shown in yellow. Okay, and then here's some examples then of the fully trained agent compared to what you get with a prior that simply wants to pick up the object near its center of mass, or an imitation learning approach. And here is the dexterous video-informed prior, or DexVIP approach that we're proposing, and it's starting to do human-like actions thanks to that video learning. Same thing for a second example with the hammer. Okay, human-like, not 100% human, I think we could agree, but getting good progress towards the dexterity needed and the generality needed to pick up new objects. And this does play out in terms of accuracy as well. The policies trained with RL without the prior versus those with simple priors or even imitation are less accurate or less successful for these tasks compared to the human-informed agent. Okay, so I'll stop here. I have talked about how we can think of objects in the open world in terms of caring less about what they're called and more about how they work. And I gave you a few examples from our work, including the hotspots, activity contexts, and dexterous grasping. And all the work I shared today is done with Tushar and Priyanka, who you see pictured here. And I would point you to their papers for even more details if you're interested. All right, thank you so much, and glad to have any comments or questions.
Yeah, thank you, Kristen, for very nice talk. So let me take a look to see if we have any question from the audience. So it seems there are no question. So your perspective on the open work in the tree work is very interesting. So for the last one, so mainly your reinforcement learning agent, I mainly look into only visual signal, right? So do you think maybe the agent can be benefit from other modality touch or kind of sensing of the objects or
definitely. Yeah, and I didn't describe the model in much at all, but we are using touch as well. So you have a reward for getting parts of the hand close to the object, and in our case, close to the affordance region of the object, and you get to use the tactile sensors to know when that's happening. We also are using the depth of the object, so not just the RGB, but the depth, so that we can have some 3D on the object, and this allows us to track the affordance as the object gets moved around. So we might predict it when it's on the table, but then keep track of it as it keeps moving. So those are the additional modalities, as well as, once you have a robot, you can, you have proprioception, so you also know how the hand itself has moved because it's its own body.
Got it. I got it. And for your first task, for the affordance, is it the task that you define and you annotate, right? And then the training is just learn to how to predict the affordance given the visual appearance or something?
Yeah, I'm not sure I caught the first part of the question. Could you please say it again?
Yeah. So the first one seems to you discover the object interaction, but that means how do we evaluate them? So
Oh, yeah.
yeah.
Yeah. So 2 ways to evaluate. I mean, the one that I showed in that table was against human given ground truth. So
Yeah.
saying, where those are. Now, maybe 3 ways I'll mention. So that's what was in that table, but you might say, hey, that's getting back to that issue that I complained about, which is that, annotators had to do this and they have a gap in their understanding. So other ways that can be done, one, in separate work with the grasping, we made use of contact DB. This is a cool data set from researchers at Georgia Tech where they had people hold objects and then use a thermal camera afterwards to see where they touched them. And this is at least this is possible for grasping, right? As affordance of grasping, because now you get really the ground truth of how the people touch the objects. So that's another way. And then the third way is really downstream, just saying, well, we'll say these affordances are useful or they've done their job if they enable better functional grasping of an agent or some other, agent action task. So that's just another way to say, are the maps we're producing useful?
I see.
And then that, the hypothesis being the more human-like they are, the more useful they can be.
I see. And then it seems to be generalized well from one data set to the other one, but I wonder if it's just like more for now, like work only on the object that we know, or it's also like the novel object, like for this one?
Do you mean for the hotspots or for the grasping or kind of both?
Yeah. Let's say for the hotspot, let's say.
Yeah, so we do separate out that evaluation at the category level. So meaning, of course, every instance that we test on is new, but also we do a test where we divide so that categories are new.
I see.
Now, of course, there's a limit to like how new can they be, so the kind of things you can expect to translate are part level things. So like if I start to understand, that a handle on a door is like a handle on a drawer, even though they have different orientations and they're not as big as each other, or handles on objects. So at least we do quantify that generalization, but I think what we have to keep in mind is the translation will be possible if there's shared parts and structure, and maybe it's especially important that the model can pick up on shape for this use, because often that's a driving factor as opposed to the texture and an exact appearance of the object.
Okay, great. Thank you so much, Kristen, for giving the talk. And thank you again. So,
sure, yeah. Thank you for having me.
Yeah. So the next in the schedule is Weiyao presenting the competition result. Yeah, you can have the slide. Thank you.
Yeah. Yep. Can everyone see my screen?
Yeah.
Cool. So first, thanks again for participants to come to our workshop. So now I'm going to introduce a bit about the challenge we hosted this year, as well as the results summary. So this is the outline of what we are covering today. So first, I'll continue those opening remarks to give a deeper introduction of the UVO dataset, which stands for Unidentified Video Objects. It's designed for open world. And then we'll go a bit on the summary of the challenge, like the different tracks we hosted, and what are they exactly. And finally, we'll announce the winner, and the winner will give us a presentation on how they approach the problem. So I'll recap on this a little bit. So do talk about this in the opening remark. So why do we care about open world? There are at least a few areas. First, we want the ability to handle novel objects. This is the key to embodied AI, such as robotics or autonomous driving. And on top of that, this will help us to open the open world visual reasoning problem. And in addition, because now with open world detection and segmentation, you can reason on objects or entity. This will enable video understanding beyond short clip and beyond simple tasks like classification. So this motivates us to approach the open world problem. Well, as Stu already mentioned, like what we would ideally like to solve in the open world problem, right? So open world requires at least two things we found. First, we require a data set that exhaustively annotate all objects that present in the video and track them. And second, such annotation ought to be taxonomy free. Why is that? Because we don't want to be biased towards specific categories or specific set of objects. By adopting a taxonomy-free approach, this actually unblocks the first part, which is that we want to exhaustively annotate everything that are present in the video. So this is exactly why we built the UVO dataset. It's designed to study the open world problem. So in the UVO dataset, it contains a dense set and sparse set. Both of them offer exhaustive annotation of all objects. The only difference is that the dense set is annotated at 30 FPS, so very temporally dense, and it involves lots of efforts to make sure objects are tracked correctly. And then there's a sparse set where we go for scale on diversity of videos, but they are annotated more sparsely at only 1 FPS. As Stu already presented that many categories are actually not covered in the typical AT COCO categories. Almost 60% of the instances are out of taxonomy in COCO. And because we annotate everything densely, on average, there's 13.5 unique object instances on average per video, which is, as we'll see later, significantly more than other existing data set. And the source for UVO is the YouTube videos we adopted from Kinetics dataset. Oops. Here are some example annotations. As we can see, we try to annotate every object density, and even some of them is very hard to recognize just from the image, what they are. But since the annotators see this as a video, they see that the pixels move together, so they were able to actually identify things that don't even know what their categories are. This is the statistics UVO present. As we can see, compared to previous video dataset that focus both on segmentation and tracking, UVO offers a significantly larger number of objects per video or per frame. As a result, UVO has lots of complex scenarios, such as crowded scene, motion blur, that is not very well covered in previous dataset. And even comparing to the well-established image dataset, COCO 17, the average objects per video, or to compare per frame, is almost twice as large as COCO. This is a result, again, as we exhaustively annotate all objects. In addition, we show that UVO is very challenging. We run the mask track RCN baseline, which is a video instance segmentation baseline. It requires you to both detect, segment, and track an object on a video. On all metrics we are seeing here, comparing to the performance on YouTube VS, there is a huge drop in performance on both recall and precision. We know that even you fine-tune on UVO, the dataset itself is still much, much harder than the existing video instance segmentation dataset from YouTube VS. So are we hopeless in this? Well, not exactly. We present an alternative, which is bottom-up super voxels. The super voxel methods, because they don't require any training and they're parameter-free in that sense, they shouldn't be much biased towards what are seen or unseen because there's just no taxonomy in them. We adopt this bottom-up approach called graph-based hierarchical grouping, GBH. And because there's no ranking in super voxels, we use an approximate version to compute average recall. This isn't a fair comparison to the top-down approach of mask tracker CN, but still we see a small gain by using the bottom-up approach, where there's not much bias between objects that are seen in training data and unseen in your training data. So that wraps up a brief overview of the UVO dataset. Now I'll jump into the challenge overview, the challenge we hosted this year. So here are some key numbers I hope audience can take away. 40. This is a 40 days journey. We started the competition in late August and wrap up in early October. The competition lasts for 40 days. 120. We received 120 valid submissions on test server in total. 20. There are more than 20 teams initially interested and registered for the challenge. 8. We have 2 tracks, and there are 8 participating teams in the first track, which is frame-based. 4. We have 4 participating teams in the track 2, which is the video track. I will explain what different tracks means in the next slide. So first for track 1, which we call this frame track. This basically adopts the frames from UVO datasets of the sparse set, where it is annotated at 1 FPS, but still densely with all objects annotated seen annotated. The task we take is class-agnostic instance segmentation, so there is no differentiation between different classes. This ought to be class-agnostic, only objects versus non-objects. The task requires to detect and segment all instances labeled correctly, regardless of what their category is, and there's just no category because this is class agnostic. The evaluation protocol we used to rank participation is average recall at 100. So basically, this will be the average recall at multiple 2D IOU thresholds with maximum of 100 detections and load. Because we have about 11K videos in the sparse set, we divide them into train, validation, and test. Both training and validation data can be used to compete for test set. So this represents the leaderboard on track 1. We have 8 participants in this, and actually the top 3 participants are very close in their final performance. For the track 2, which is the video track, we use the videos from UVO dataset, and this is the version 0.5 from the dense set, which is annotated at 30 FPS, different from the sparse set. This involves the class-agnostic video instance segmentation problem. So different from image instance segmentation problem, on top of detection and segmentation, it requires you to track an instance correctly and consistently across the whole video clip. So it's possible that the instance may disappear and reappear, or disappear and be gone forever. So it requires you to handle these cases. The evaluation protocol we adopted is very similar to what we did for the image track or frame track. The only difference is that instead of having the 2D IOU, we use the 3D IOU, which also considers, besides the 2 spatial dimensions, we consider a temporal dimension here. The version 0.5 only contains around 500 videos, and we split them into train, validation, and test as follows. And both training and validation can be used to compete in the test set. So we have 4 participants on the second track, which is the video track. The top winner significantly outperforms the rest of the participants, but we also know that all 4 participants almost double the baseline from mask tracker CN, which is very impressive. This shows there's huge potential we can improve on the video instance segmentation task in the open world. As people would see already, both frame track and video track, we have a single winner for both tracks. The winner are Yuming, Wen, Yang, and Vincent from France. Congratulations to the winners for scoring top on both tracks. And now I will give the floor back to the winner to share how they approach the problem, and hopefully this will inspire more research in open world. Yuming, do you want to share your screen and go ahead?
Yeah. I'm going to okay, so let me share my screen. So can anyone see my screen?
Yes.
Okay. Sorry. Just yeah. Great. Okay. Sorry. Okay. So I'm going to start here. So hi everyone. My name is Yuming, and today I'm going to talk about our methods for winning the UVO challenge. And our team is affordances. So we have participants patent to two challenges. The first is image-based open world segmentation, and the second is a video-based open world segmentation. And first, let's begin with the first challenge, the image-based open world segmentation. So for this challenge, we have adopted a two-stage instant segmentation framework. So first, an image is fed to a detection network, and then the detection network will predict the bounding box proposals. And together with the image, we feed it to the segmentation network, and the segmentation network will predict the masks. And the advantage of our pipeline is that we can train the detection network and the segmentation network separately on different datasets. And the second, with a large input size of segmentation networks, we can have finer and better mask predictions. And the third, according to a recent paper, in this way, we can generate more accurate masks for unseen classes. And first, let's begin with the selection of our detection networks. So we need to choose a baseline network, and we compare with three methods. The first is a fast RCN, and the second is a cascade region proposal networks. And second is the object localization network, which is presented by our first speaker, Dahan. And we train all these networks on COCO dataset and evaluate on COCO minibar and the UVO sparse validation datasets. And as you can see that the cascade region proposal networks achieve the best performance on both datasets. So we choose the cascade region proposal network as our baseline network. And then here is an illustration of our network architectures. And in summary, our network architecture can be divided into 4 different parts. The first is a backbone network, and second is the neck of the network, and the third is the head of our network, and with a label assignment mechanism. So for the backbone network, we replace the original ResNet 50 network with the 3 large transformers pre-trained on ImageNet 22,000. And for the neck, we add, instead of using only the feature pyramid network, we add the Karov block in the feature pyramid network for better feature upsampling. And for the head, instead of using the cardboard head, which means for the classification head and the regression head, we share the same COM layers. We use the decoupled head, which means the classification head and the regression head use different COM layers. And in addition to these 2 heads, we also adopt LU branch on the top of the regression head. And for the label assignments, instead of using the simple IOU intersection over union matcher, we adopted a modified version of Smota assigner. And so the idea of the Smota assigner is that between the predicted bounding box and the ground truth bounding box, we define a cost for the matching, and we only select the top K predicted bounding box as a positive samples. And in addition to this, we adopt different positive and negative sampling strategies for classification and regression. So in particular, for the regression head, there we assign more positive examples during the training. And here is the avalanche study leveraged on the COCO minibar datasets, which show that starting from the region proposal, a single region proposal networks with ResNet 15 backbone, in the end we can increase the average recall by 26.1. And for the segmentation networks, so we adopt the AffordanceS as our network architecture, and we use the swing large transformer as our backbone network. And our segmentation networks aims to predict masks given a cropped image. So the pipeline is given a bounding box. We first use a bounding box to crop the image to crop the image and get the image patch. Then we resize the image and feed to the segmentation network. Then the segmentation network need to predict masks for the image patch. So it's a binary segmentation tasks. And the training details is that for the training details, our detection networks use ImageNet and COCO datasets for pre-training and fine-tuned on the UVO sparse and UVO dense datasets. And for our segmentation networks, it has used the ImageNet, OpenImage, and Pascal VOC and COCO dataset for pre-training, and it has been fine-tuned on the UVO sparse and UVO dense datasets. And all networks are trained in a class agnostic way. And here are some qualitative results on UVO test datasets. So this qualitative results is made by given an image, given a bounding box predicted by our detection network, and our segmentation network will predict the masks for the object in the bounding box. So as you can see in the images, our methods can predict some great masks even when there is some strong occlusion or the motion blurry. And here's the qualitative results on the UVO test datasets. We have achieved the best performance on the UVO test datasets. And that's all for our method for the track one for the image-based open world segmentation track. And for the video-based open world segmentation, our motivation is that with high-quality mask proposals, a simple matching mechanism is good enough for tracking. So our pipeline is similar to the IOU tracker. So given some trackers from frame T-1, so from previous frames, and then given some mask proposals for the frame T. So the mask proposal is generated by our two-stage instant segmentation framework. And we first use the optical flow to warp these masks, the latest masks of the tracker to the frame T. And then we just use the intersection over union to match the warped masks with the mask proposals for the frame T. And then if the masks of the trackers has been successfully matched with some mask proposals, then this matched mask proposals are used to update the masks of the trackers. And if there are some masks proposals that has not been matched, then these masks are used as to initialize the new trackers. And if there are some trackers that has been continuously not matched for several frames, they will be removed. So that's a pretty straight and simple matching mechanism. And for the score of each tracker, we calculate as a product between the number of frames being tracked and the sum of the detection score. And for the optical flow, we just use the Raft network for optical flow estimation. And here is some qualitative results on the UVO test datasets. As you can see that our two-stage instance segmentation framework already predicted some masks with great quality. And so by using only the optical flow, we can track some network, some objects with complex shape, like the net in the tracker one. And also for the quantitative results, we have achieved the best performance on the UVO test challenge. And so in summary, first, we propose a two-stage framework for instance segmentation. And second, a simple matching mechanism for video instance segmentation. And for the future work, first, maybe we think maybe it is beneficial to add more training data for the detection networks, because now we have just trained our detection network on the COCO dataset and the UVO dataset. Maybe adding some, for example, open image or object 365 might further improve the detection network's performance. And second, because now we just adopt the simplest data augmentation for our detection networks and also for the segmentation networks. Maybe adding more data augmentation might help to further improve the performance. And third, it's obvious that our tracking method is a bit too simple. So maybe a better tracking method might help to further improve the results on the video track. And first, I noticed that in the UVO dataset, there are some really tiny masks that's with the error smaller than 10 pixels. So maybe during the inference or during the training, we should pay more attention to the smaller objects. Yeah, so thanks for listening. Especially thanks to UVO team for creating such an amazing dataset, and it's really helpful for our research. And our code will be released in this link. So thanks all.
Oh yeah, thanks again for the nice talk, and congratulations again for winning the challenge. So it's very solid work. So actually you just answered one question I have on the Q&A. So in the Q&A we have one that asking either code available for testing. So you just answered it now. So but I have the next question for you. So have you ever evaluate runtime, like how efficient the model is, like how many FPS you can run on video, like for inference?
Oh, yeah. That's a good question. In fact, I think that's really maybe an issue for our proposed method, because we adopted two networks separately for detection and segmentation. In fact, the problem is that with this pipeline, the inference time might be very long. So the inference time is not so compare with some end-to-end training, end-to-end networks. For example, the master scene or some larger instance segmentation networks. We are certainly slower than these networks, and but I think this might be improved if, for example, we can just decrease the size of our segmentation networks, and for example, and end it to the detection network and use it as like just a max branch of the detection network, and that might accelerate our networks. That's it.
Yeah, I see. And I think one other question is that because you have two-stage approach, right? You train the detection and then you train the match prediction. So do you see like any performance about it by the first stage?
Sorry,
Is it your performance is kind of like limited by the accuracy of the detector at the first stage you use?
Oh yeah. In fact, if I understand correctly, your question is about the bottleneck of our methods.
Not really bottleneck in terms of performance, but let's say, you can think about bottleneck in terms of like accuracy, because let's say if your first stage detector already missed them, then there's no way for the second stage to produce the mask from it, right? And you see that is huge, or let's say which one can give you more opportunity to improve? Like if you want to go back, whether you want to invest more time to improve the first stage or the second stage, which one? My feeling is that maybe your second stage do very well already.
I think in fact I think the problem mainly comes from the second stage. In fact, so because I tested our methods on, for example, I tested only the detection networks on the UVO validation datasets, and the record is already good enough. The record, for example, with the test time augmentation, our record can obtain it's nearly 80 for the average recall top 100. So I think the record is already good enough for the bounding box, but it's mostly the segmentation networks. Sometimes, for example, because that's also an issue for our proposed method. Is that, for example, if we just shift a little the bounding box, and the predicted mask can vary, can have a big, how to say, to vary largely.
I see.
So, for example, so if there are two persons overlapped, and we just shift the bounding box around, and the masks mainly vary from one person to another. So that will certainly affect the final performance. And for example, we have also added some tested with some test time augmentation with our segmentation networks, and all of them didn't work. So that's...
I see. Yeah, great. So there's another question on the Q&A. So from Akos, have you observed some typical failure case, for example, irregular shape?
For that, I didn't notice this type of filter case, but I did notice a type of filter case is that, for example, if our bounding box is too big, it's too large, the segmentation networks tend to predict the background masks instead of only the foreground masks. So, for example, if there are a person in the image and our bounding box just cover the whole image, and the segmentation network will predict it. Will segment the background of the person, and takes the person as a background. So,
I see.
That's one future case. So except that, I think it's good enough for all the objects.
So I see. So it's more like you swap the background and the foreground. But let's say if you provide both of them, let's say you still can have improve your performance. But by the way, so it seems like, to your experience, the challenging problem is on the prediction mask, not the first stage, right? And then okay. So that is very interesting observation. So Weiyao, it's more like seem like a problem of box to mask, right? Even a box and then produce a mask, because we also observe similar case like for some very complicated occlusion case, confusion between background foreground understandable, and it's just like the concept of what you are looking at. Okay. Let me take a look at
another question. Have you tried with not using the open image, or just focusing on using Coco dataset for the frame part pre-training?
That's a good question. In fact, because there are yeah, because we did the challenge in a rush, and there is not enough time to do so much experience. So we just use all the datasets that we are capable, and the idea of using the open image is that as the open image, it contains many object classes, and we think that maybe it can be helpful to segment for example, especially for the UVO challenge. But yeah, it's a good question. So maybe we can do it later to see that if we remove the open image dataset and how the segmentation network will perform.
Great. So yeah, thank you again and congratulations. We will follow up with you for the award and on kind of logistics. But yeah, again, congratulations. It seems that we are a little bit ahead of time. We have like 9 minutes, so let's give everyone like 9 minutes short break before we come back at 10:45 for the third invited talk. So see you everyone in 9 minutes.
That's it.